Okay, I think I'm gonna get started because I have a ton of content. I'm here to talk. So my name's Jake Wharton. If you missed the keynote, and I'm here to talk about a few OK libraries. And what this means is libraries, the OKIO library, and libraries which are based upon it, and kind of how being based on OKIO and using OKIO is extremely advantageous to them, and how using them together really creates this efficient pipeline. And so this is going to be it's going to be very technical and very kind of deep talk on the innards of OKIO. So I'm not really going to cover like how to use OkHttp's API or Retrofit's API. We're going to talk about how these libraries interact with each other and kind of why you should use them. So OKIO. OKIO is a library for bytes and for text. And it is a complement to the Java IO and Java NIO libraries. And basically things. It's around, it's built for accessing, storing, and the processing of data, be it binary or text. And OKIO is really a foundational library. This is something that you build on top of, that you're not really interacting with kind of at the higher level in your application. Usually you're talking to libraries which are going to be built on OKIO. That's not to say that types from OKIO might not be exposed higher level in your app, but normally you're going to be talking to libraries that are built on top of them. And so there's three today that we're going to cover: OkHttp, Moshi, which is a new JSON library, and Retrofit. So let's get started with OKIO. I spent a lot of time with Magic Move. Okay, so why OKIO? Why is this needed? Why is Java IO and why is Java NIO not sufficient enough? And to kind of convince you of this, I don't want to tell you why, I want to convince you why. And to do this, I'm going to use HTTP, because HTTP is how OKIO came to be. The OkHttp library was using Java IO, so input streams, output streams, for processing HTTP. And this turns out to not be sufficient. And we're gonna take a look and we're gonna see why. So we all hopefully know what HTTP looks like. It's text-based requests and text-based response. And usually this is how it's presented. And every engineer kind of has this level where they assume everything underneath me is like a black box. So oftentimes you don't really care how an HTTP client does this. You know it's doing this, but you don't know how. You don't exactly know how it's doing the processing. Or maybe you do, and your black box is a little bit deeper. But if HTTP is kind of where your black box is, if you just use the APIs, we're gonna push that black box deeper and really see how this works. So when you look at like Wikipedia or whatever, this is what you're gonna see. And what they're not showing you is what's kind of in between this text, and that's the spaces and the new lines. And these are extremely important because this is how the response is processed. And unfortunately, they always show it to you like this with these nice lines, which is actually not how it looks like when it comes across the wire. It's more jumbled up like this. So every time we're like reading data from a socket, which is speaking HTTP, we're just going to get these globs of data, and we need to turn them into something that's processable. And so as a human going through this exercise of parsing the protocol, the way that it works is we're just going to look for the first new line. We're going to start at the top left. We're going to scan across and look for our first new line. And then everything before that, we're going to split it on the spaces, and now we have our first three pieces of the HTTP protocol: the version, the response status code, and the message. So this was success, yay. And then we just continue. We go, we look for, we scan the rest of the first line, we move on to the second line, we find our next new line, we take everything before it, and because the HTTP protocol defines that the first line is the status, and everything after that is going to be a header, we know that now we need to split on a colon and a space. So we just take those two pieces of data, and now we have our header, and this is what we do over and over again. And it's really easy to reason about this as a human, but how would we implement this as a programmer using Java IO? Well, input stream is the canonical way that we parse data. It's got a couple of methods that we all know, like close, of course. It has a skip method, Skip method is actually deceptive. A lot of people don't notice it has a return type of long. You might tell it to skip 10, it could only skip 4. So to actually use this skip method, input stream is already placing burden on you, the caller, by forcing you to loop every time you want to skip. So you either have to, every time you call it, loop yourself, or throw some utils method somewhere that does the loop for you, and always remember to call it. So we're 2 methods in, and we're already seeing some faults with input stream. Next, we have our read methods, and we have 2 of them. We bring our own byte array buffer, and we can either just give it the whole buffer, or we can give it a subset of the buffer to write into, and it's going to return how many bytes was read. And thankfully, when you're implementing this, you actually only have to implement one of them, the second one, because the default implementation will call that automatically. So that's nice. Well, except I forgot that there's another read method, which only reads a single byte. And you actually can't get away with just implementing one method. You have to implement 2. You have to implement this one and the batch one, because by default, the batch one's going to call this method for every single byte in that buffer, which is extremely slow. So that's annoying. Now we have to implement 2 read methods. And most people would think that this is kind of where input stream stops, but it actually doesn't. It has these whole other methods which have really nothing to do with purely reading data. These are for doing simple buffering. So we can see how many bytes are buffered in the stream, are available, and then we can use something called mark and reset, which allows you to kind of rewind a stream. And if you're implementing input stream, you can simply return false for mark supported, or you're forced to implement all these methods. So this interface is a lot more complicated than it should be. And despite you might know buffered input stream, so you would think that that's the place where these methods should live, not on input stream. So despite not being an explicitly buffered type, we still have all these buffered-like methods that every input stream has to support. So our API, just to summarize here, our first thing we know about Java I/O is that we have multiple concepts and inconsistent behavior already in the API. Let's look at what it would take to kind of move on in a Java I/O world for parsing this response. So this would have been in a byte array, and it just so happens that it fits perfectly in the byte array, which means that we can clear it and move on to our next headers. So each one of these lines is basically going to be a read call. So we're going to read the rest of the line, the second line, and get part of a header. Now after doing this, we're going to have to scan for that new line. So we scan from right to left, and we see there's no new line. Well, that's unfortunate. Let's do another read again. Pull in more data. Now we have to scan again. Naive implementation would scan from the beginning, or you could scan from where you left off, and we still don't have a new line. So let's perform another read. Now we can only read part of the data that's available in the socket because we, the caller, have a fixed size byte array that we had to supply to input stream. So we got half of the next read from the socket. But hooray, we found a new line. Let's go back, find our colon, and split it. So we found a header. Now we're left in a pretty interesting predicament because we have data in our byte array, but it's at the end. So what could we do here? Well, if we were naive, we could just create another byte array, copy the data, throw away the old one, and then continue on with our new buffer. As I hope you can realize, this is extremely inefficient, and we would not want to do this every single time we have data left over in the buffer. Another way to do this would just be to keep track of where our data started and where it ended. So we have our pointer, and we have one that says we stopped at the end of the byte array, which can really also be thought of as the start of the byte array. So when we call for more data, we just start filling in from the red position. But you'll notice that after our read, we still don't have a new line. If we go from the green, and we wrap around, we don't have our new line, so let's do a read again. We only have a couple bytes left. We've now filled our buffer, and we still don't have a new line. So yet again, we are put in an awkward predicament. What do we do here? Well, we could double the size of the buffer, copy our data over, do another read, and this is going to happen over and over again. You really can't know how large the buffer is going to be in order to do this processing. So once again, input stream is placing undue burden on you, the developer, for what is otherwise a relatively simple task. Thankfully, there's what's called decorator classes for input stream that you can wrap them with. And so I alluded to the buffered one earlier, and this is actually going to help us out for making our reads more efficient by having a larger buffer between us and the socket. So when we do a read, the buffered input stream is going to read a ton of data and allows us to efficiently do reads against that buffer. However, we're going to run into the same problem where because we brought our own byte array that was inappropriately sized, we still can't fit a header in a whole buffer. So while you have this ability to decorate your input streams with, say, a buffered input stream or potentially one that's doing gzip, you're still having to figure out storage yourself, the byte array. The other thing about input stream is dealing in byte arrays is not always the most efficient way of doing things. Often you want to look at kind of higher level views of what the data is. So there's a class called data input stream, which gives you all these really helpful methods of taking, say, 4 bytes and turning them into an int. This is great. This is another decorator that you can wrap around your input stream. However, you'll notice that while there are methods that return strings, they parse a special version of UTF, which can only be written by a data output stream. So if you have just text on the wire, you're still not able to extract, say, 4 characters of it as a string. Well, there's another decorator for that called input stream reader, which does let you do that. And this is also a decorator around an input stream. But the problem here is that both of these cannot be used. So in HTTP, we have, say, the HTTP 1.1 string that we want to read, and then we have the 200, which is an integer that we want to parse. And if we want to do that with these higher level APIs, we cannot, because we can't use both of these decorators on the input stream because each one is going to be independently buffering that data. I know I'm going a little fast, but I'm just trying to destroy your view of input stream. So while input stream Java I/O has these high-level abstractions, they don't compose together. So let's get on to OkIO and how it fixes these problems. Like I said, it complements Java I/O and NIO. We want to interop with these because they're in your libraries, they're in the JDK, they're unavoidable. So we need to interact with them, but hopefully you'll view this as a replacement in your application code. There's two of the main types. The first main types that we're going to look at are called source and sink. These are the complements to input stream and output stream in NIO. So you have a source of bytes and you have a sink for bytes. Read from a source, write to a sink. If you're familiar with Guava also has classes called source and sink, which behave similarly. So let's look at its API. We have our tried and true close method. We have something called timeout, and timeout's pretty unique because it allows you to specify how long interactions with this source can take. And this can be done in individual operations. I can say, when I do a read, I don't want it to take longer than 5 seconds. Or it can be done in deadlines. You can say, every interaction I make with this source has to complete by the current time plus 60 seconds. We have a read method, only one read method. This takes a class called buffer, which we're going to look at in a second, a count of bytes that you want to read, and the number of bytes read. And you'll notice that while we're still providing our own buffer to this class, it's not a primitive byte array. So we're not allocating. You'll see we're not going to allocate a size for this buffer up front. And that's it. Those are the only 3 methods. So if you're implementing this source, you don't have to deal with multiple read methods. You don't have to deal with the awkward buffering methods. You don't have to deal with the weird skip method that doesn't necessarily skip the value that you give it. Sink is the counterpart. This is where we write data. It's basically the same thing, except instead of a read, we have a write. And there's also one more method called flush, which if you're familiar with output stream, same exact semantics. It just pushes all the buffered bytes down the chain. Okay, so source and sink. So we saw a buffer in that class. There's two classes for holding data in OkIO. Buffer is the main one, which is a immutable data store. And there's something called byte string, which I'm actually not going to cover, but it's just a immutable set of bytes. So the behavior of buffer is what's most important to understand in OkIO, because it's really the core of how data moves around in the library. Allocating a buffer is cheap. It actually does no allocation of data storage. So the only penalty for allocating this object is the cost of the object itself, which is relatively lightweight. And basically what a buffer has is a pointer, and by default it points to nothing. So let's say we want to, in the way that the way that data storage works is that there's a pool of what are called segments. And this is where the actual storage mechanisms lie. And buffers are going to borrow storage from the pool and return storage to the pool when they're done with it. If you've ever interacted with some platform types like touch events or with messages with a handler, you know it's basically the same operation, or any pooled mechanism. But thankfully this is all completely transparent, which we'll see. So let's write some data into our buffer and see how it behaves. So we're going to steal, or I shouldn't say steal, we're going to borrow a segment from the pool and update our pointer in the buffer to point at it. And then we just write our data in. And these segments are immutable, so we can write directly into them. It's a very cheap operation. And so we've written into our byte array, and now we've just bumped a pointer that says we start at 0, and now we end at 15. Similarly, we write again, the same thing happens. For the purposes of this talk, we're going to pretend like these segments are, say, 32 bytes. But in reality, the byte arrays are a lot bigger, and that's actually an implementation detail that could potentially change at any time. So if we need to write again, we only have 2 bytes left in this initial segment. So the buffer is going to grab another segment from the pool in order to basically expand the storage that it has. And then we just write into that segment. Reading works the same. Oh, by the way, these methods that are on buffer, I'm going to cover in a future slide, so don't get too kind of bogged down on how they behave or what they do. When we read data from a buffer, basically it's the same operation in reverse, except now we potentially don't have to do as much copying. In this case, we're reading a string out, so we will actually have to copy this into a new string object. But all that has to happen on the segment itself is we just say, instead of starting at 0, we just read 5 characters. We're just going to update this so it starts at 5. Extremely cheap operation. Similarly, if we now read the rest of the first segment, the position is going to get updated. And now they're the same, right? There's no data inside this first segment. So what's going to happen is the buffer is going to return that segment to the pool for other buffers to use, and it's going to promote the second segment to be the first segment, so that the next read that happens will happen from the first segment. Now, a really interesting behavior, and again, one of the kind of core fundamentals of how OkIO makes things efficient, is when you're moving data between buffers. Because this is what we saw when we had our buffered input stream and our input stream. Each had a buffer, and we had to move data between the two. OkIO makes this operation extremely cheap, because when I have this other buffer, and I say, take everything from my initial buffer and write it into this new buffer, all we have to do is basically change 2 pointers. We null out the pointer in the first buffer, and we set the pointer in the second buffer to that segment. So we've just transferred the segment. No data copying has occurred of the byte arrays, and there's no additional storage needed. So where this gets really powerful is when these two things combine together. And so OkIO has these 2 types called buffered source and buffered sink. And these move data, but they move it efficiently by using this buffer object. And this is where those methods on buffer lie. So there's tons of write methods. These are the high-level abstractions that we saw earlier with input stream, except you will notice that we not only have primitive methods for integers and longs, whether they're big endian or little endian, but we also have ones for still moving byte arrays or our strings in various character sets. Buffered source is the same way. This is how we read high-level data. So we can read strings, we can read longs, we can read even byte arrays if we wanted to, both from the same object without having to decorate it further. And we'll take a look at kind of some of these in subsequent slides. This actually isn't all the methods on each one. There's a little bit more to deal with housekeeping. You can actually get access to the underlying buffer. And a very important one is you can observe any buffered sync as an input stream. And you can observe, or you can turn any buffered source into an, oh, I got that backwards. You can turn any buffered sync into an output stream if you need to pass it to a JDK method or something in a library. And you can observe any, or turn any buffered source into an input stream, additionally to pass to any library that is using input stream. And what's really cool is that buffer itself is actually both a buffered sync and buffered source. And so this is what we saw earlier on when we were reading and writing data into the buffer object. So this is a mutable data store with high-level methods for primitives, for strings, and even for raw data through byte arrays. Okay, so when you're interacting with like lower level data sources, OkIO is going to make those extremely efficient by kind of hiding away all the buffering that's going to happen inside these buffered sources and buffered sinks. So this is our socket, and we're going to fill our socket with data. So this is a HTTP request, or a response rather, from our first slide. And we're going to sit our buffered source in front of it. And now we're going to go and we're going to start parsing our HTTP response. And the buffered source is going to read a large chunk from the socket, and then it's going to use those high-level methods to pull parts of the bytes out at a time. And you'll see when we get to the point where we need to read more data, it's going to borrow a new segment, pull in another chunk from the socket, and then just transparently keep going and return the first segment when it's complete. This goes on until we finally exhaust our last segment, which ultimately then gets returned back to the pool. And so our calling code, this is our calling code on the left. We never dealt with storage. We never dealt with borrowing segments or returning segments. And yet, automatically, with our interaction to this socket from a high level, we basically got away with never allocating a byte array and only doing 2 copies from the socket. And yet all we had to do was use this high-level API. So hopefully if you've ever dealt with things like parsing some low-level protocol like HTTP or maybe WebSockets or HTTP2, something like that, you should be kind of drooling when you see something like this, because when you do it with input stream, it's really just terrible, and it places a lot of undue burden, again, on you as the developer. There's this final class I want to talk about in OkIO before we move on to how the other libraries integrate. And it's a class named OkIO. And this is sort of the central place for adapting different OkIO types and different platform types into one another. So when we have a source and we want to turn it into one of those buffered sources with the high-level API, we do it through static methods here. When we have our input streams, we have our output streams. This is what allows us to get a source and to get a sync out of those. We have special ones for socket that deal with applying the timeouts natively to the socket, which has to be done a little differently than just a normal input stream or output stream. We of course have ones for dealing with Java IO file and Java NIO paths, which is really only for JDK 7 and up and not Android. And I'll also note while I'm on this slide that you'll see a lot of times we just deal in sources and sinks, which is not It's not the type that you really want to be interacting with, but it is the type that you want to move around. And so usually you'll be passing around sources and sinks, but you'll be immediately calling into this class in order to wrap it in a buffered source and buffered sink. And so as we saw, creating a buffer is an extremely cheap operation. So the fact that you might have multiple of these layered on top of each other, because they're really not doing allocations like multiple buffered input streams would be doing, and they're not doing data copying as data flows through those different layers, they're only moving segments through each other. It's an extremely cheap operation. It should be considered a best practice. So just like Java I/O, OkIO also has decorators. The two that we provide in the library are ones for doing the inflate and deflate, which are also in Java I/O, and then gzip, both compressing and uncompressing. So let's take a look at a quick example of what this looks like, or something that uses this, rather. So we have a file, arbitrary file. Oop, we have a file. We're going to use our static factory method, and we're going to turn this into a sink, because we're going to write data into it. We wrap that in our gzip sink. So this means that any data that gets written into this sink is going to be gzipped and then written into the sink for the file. Like I said, no one wants to application code or code that's interacting, reading and writing doesn't really want to deal with source and sink. We really want to deal with buffered sources and buffered sinks. We want that high-level API. So we're going to wrap it in our buffered sink. So now when we write some code, it's going to get held in the buffered sink. And this is because we haven't written enough to fill a whole segment, which means that segment's not going to force its way down the pipeline yet. We could call a flush here, but I'm simply just going to call close. And this is going to send our data into the gzip sink, which is going to gzip it, and then it's going to send it into the file sink, which ultimately writes down this gross-looking gzip string into the file. So a few lines of code, and we've now basically written something that does transparent gzip with a high-level API. So in addition to the ones that we provide, you can very easily write these decorators yourself. So in this example, I have a hypothetical sink, which is not going to mutate the data passing through it all, but it's going to compute a hash of all the data that flows through. So even though that the sink kind of is sitting in this pipeline, it doesn't have to actually modify any data, but it can observe it. So in this sink, basically everything we write into the buffered sink gets passed into the SHA sink, which is going to compute a hash. And then after I've closed the sink, I can then read the hash out from this sink for use as an HTTP header or another file as a signature for what we've written. Another really cool example is rather than modifying the data that flows through or observing the data that flows through, we can actually change how the data flows through, such as with speed. So let's take a socket and we'll wrap it. And we create a hypothetical class called throttler. And the throttler is going to take our socket source and it's going to create a throttled source. And you'll see this is still a source, so the throttling is an implementation detail. We buffer that source and we read 10K from it. And so by default, our hypothetical throttler is not going to do anything. And it's just going to let this data flow through as fast as possible. So this will take, a few milliseconds. But what we could do is have our throttler have a method to rate limit this API, to introduce artificial rate limiting. So we say, hey, I only want you to allow 50 bytes for every second to pass through this sink. And it's going to hold in its buffer any data beyond that. And so every second it will emit 50 more bytes. So now when I read 10K, it's going to take whatever, minutes, days, quite some time. And so this is actually really interesting because it allows you to simulate network conditions without actually affecting anything in your data pipeline. And so this Droidcon class is actually not hypothetical. It's something that we're going to be open sourcing next week, 2 weeks. It's almost done. Basically just wrapping it up. We're not quite sure where it's going to live. It might be in OkIO itself, or it might be its own project, but it's something that we're using to very easily simulate poor network conditions when you're otherwise connected to what is a super fast network, or even potentially local data, right? Because this source could be a file, and I could introduce an arbitrary rate limit on reading from a file to emulate like I/O contention. Okay, OkHttp. So OkHttp is where OkIO was originally conceived. It was inside of OkHttp until we kind of felt it was matured enough to be its own project. And let's see how OkHttp uses it and exposes it to you, the caller. So if you're not familiar with OkHttp, it's a high-level HTTP API. It's very straightforward. We have a client that manages, the connections and any settings that you might have around how to talk to your remote server. And then we have request and response objects. Let's start by looking at request. So this is a simple GET request. You pull down this HTML file. No data is needed here, but if we're posting, we need to supply a request body. Request body is an OkHttp class. It has 3 static factory methods for common use cases. So you have some string, you have a file, or maybe you have a byte array, and the media type is just the content type. So it's application JSON, it's text plain, whatever. Request body is actually also an abstract class, so you can implement your own versions of this. And 3 methods. We have the length and the type, as we talked about, and then we have a method to write the data to a buffered sync, and this is, as we know, an OkIO type. So we take our hypothetical request body that we've implemented, and we write it to a sync. So we have our socket. Our socket has a OkHttp is going to wrap the socket in a sync, and it's going to take care of writing the request. It's going to write, the HTTP, the GET, the path, the version. It's going to write any headers that you provided, a user agent, things like that. And what it's going to do is it's going to call your content length method on the request body. And let's say we're writing, 3,000 characters of data. And it's going to create a sync that's only going to let someone write 3,000 characters to that sync. And it's going to attach that sync to its sync. So as your request body starts writing data into the buffered sync that is supplied, it's actually going to be writing directly to the sync that OkHttp is using, which is directly attached to the socket. So while there are, I'm just going to keep reiterating this throughout the rest of the presentation, while there are layers of indirection that are going to be introduced, ultimately, because of the mechanism that buffer and buffered sync use, even though these abstractions or these wrappers exist, you really don't pay the cost of an extra layer of abstraction like you would with Java I/O. So you're writing data into this fixed length sync, which is really just doing nothing except ensuring you don't write too much, and you're writing directly to the sync, which is going right to the socket. Very efficient. And this is pretty cool because HTTP2 is starting to become a thing. And this is a much more complicated task for the HTTP client, but it's otherwise completely transparent to you as the caller. And so if we have now 2 request bodies instead of 1, in HTTP 1, these would occupy separate connections, and we'd have 2 separate sockets. In HTTP 2, we have 1 socket. But what's cool is that we can leverage the same patterns with OkIO in order to keep things simple. We're going to put something called a framed sync. OkHttp is going to put a framed sync between you and the raw sync that talks to the socket. And then it's just going to use the same mechanisms that it used before, which is this sync that just lets you write, your 3,000 characters. And without really any ceremony whatsoever, your data is going to be interleaved on the wire into these different frames automatically. So each one of these boxes would be like a segment that gets through the pipeline and written directly to the socket. And so this is reusing the same concepts as we had for HTTP 1. And again, we're adding this layer of framed syncs, but because of the mechanism of OkIO, it's extremely cheap to do so and allows us to very easily create this framed protocol on the wire. So we send our request. Let's read our response. OkHttp has two ways. This would be the synchronous way. We create this call object and then synchronously execute it. And on the response, we'd be able to read the body. In this case, I'm just printing it out. There's also an asynchronous way. The asynchronous way is preferred because it pushes the threading model into OkHttp, which lets it do really smart things with Speedy and HTTP2. But we're just going to look at this response body. So here I'm pulling a string, but there's actually lots of other ways that you can read a response body. Oftentimes a string is not suitable if you're using a binary protocol or simply don't want to allocate a string that's 100,000 characters. We have one for reader. This is the high-level API for strings. We can obviously get our input stream, which is the low-level API for bytes. You could buffer the entire thing in memory as raw bytes, but these are all not going to be the best option. And all of these are actually implemented in the same way. They talk to a buffered source. So each one of those methods is just calling one of those high-level APIs on buffered source. So if you get a string, it's just calling read UTF-8. If you call bytes, it's calling read byte array, etc. But you can get the buffered source directly. And this is the most efficient way of doing this because, again, you're talking directly to the OkIO types, which means there's no additional buffering that has to happen in order for the bytes to get to your application. So this is our response. We're going to grab the status line. We're going to grab the headers from the buffered sync that OkHttp has, which is directly on the socket. And then all we're going to do, we're going to see that there's 3,000 characters, again, in the response. All we have to do, or rather all OkHttp has to do, is create a source that sits on top that just prevents you from reading more than 3,000 characters. So there's no layer of buffering. It's just simply going to prevent you from reading more than 3,000 characters. And then we just give that to you. So you're essentially reading, when you're reading from this source, you're reading directly from the single buffered sync that is sitting on top of the socket. Whereas if you look at another HTTP client or other HTTP clients, you'll see that there's at least going to be 2 levels of buffering with buffered input streams. And in this case, we can avoid that altogether. So this becomes very efficient. And then what's awesome is that the decorators still work here. So if your response is gzipped, all we have to do is prevent you from reading more than 3,000 characters, which is going to be the gzip length. And then we wrap that in a source, which is automatically going to ungzip. This also lets us hide some of the more ugly things of HTTP. There's a transfer encoding called chunked, which means that we're going to give you we're going to say, hey, I'm going to send you 100 bytes. I'm going to send you 200 bytes, and it's going to do this incrementally rather than sending it all as one single response. And so we can just simply hide this behind a chunked source. And this source is just going to, when you call read, and you say, hey, I want 2,000 bytes, it's going to go and it's going to process each of these chunks incrementally until it finds, until it counts up to 2,000 and returns it to you. 100% transparent and without all these artificial layers of buffering. And of course, this plays great with HTTP2 on the other end, which is reading. All we have to do, similar to our framed syncs, is create these framed sources that know how to read the individual frames and then can pass it on to you. And this allows multiple responses to be read at the same time from the same socket without wasting multiple connections to your remote server, and without wasting those additional layers of buffering. Okay. Moshi. Moshi is a library that we've been toying with for some time, but have only recently flipped the public switch on about 2 weeks ago. It's essentially a modernization of the concepts that are in JSON. And so if you've ever used JSON, this will feel very familiar, but the fundamental difference is that it's built on OkIO. This means that because it's built on the same concepts of buffered sources and buffered sinks, we can share those directly with the HTTP client without having to go through those additional layers of indirection, which JSON does. JSON has to maintain its own buffer. Moshi does not. So there's two classes which allow you to do streaming. If you've used JSON streaming, these are the same names, and they behave the same way. So given a sink, we can basically just use a high-level API which corresponds to the data in the JSON for writing these data structures, whether it just be keys and values, or in this case, an array. And what's really cool is that in JSON, these are implemented as writing into a character array. And then that character array has to be flushed out into whatever underlying mechanism you're talking to, so an output stream. But in this case, these methods actually directly map into the high-level API of buffered sync. So Moshi really just becomes an API for hiding all of this kind of ugliness of constructing the JSON. We're not actually ever really buffering the data itself. The data is going into the buffered sync, and that buffered sync is going to be automatically sending these segments down the pipeline. Another cool advantage of this is OkIO actually re-implements UTF-8 encoding and decoding to be much more efficient than Java's because of the assumptions we can make with buffered sync and buffered source. And it's especially fast in the happy path, which is basically ASCII characters. And you can basically write up to a segment's worth of characters extremely quickly without paying the high overhead of Java's native UTF-8 encoding and decoding. And so JSON readers, the complement to this is the other end of the spectrum. It's a little bit different if you've ever parsed streaming JSON. You kind of have to loop over the keys as you get them, and then switch or use ifs to figure out what data you're getting and then read it appropriately. This does map directly to buffered sync, or buffered source rather, but the interaction is a little more complicated because of the looping and then actually each one of these methods, like calling next string, actually has to loop itself. So we'll just take a look at one of those. When you call next string, basically we've already seen an opening quote, so we're just going to need to read to the end quote. So this is an example of what the underlying mechanism does. We use, again, this high-level API called index of element inside the buffered source, which is just going to look for any character inside of the byte string. And you see we're using this immutable byte string as our constant, which just has an end quote in it, or just a quote rather. So we find the index of the end quote, and then we just call read string with the index. We don't have to do a starting position, because as we read data from this buffered sync, which is the S variable in this case, the position is automatically being updated. So we're always really at 0. So all we need is the index of the end quote, and then we can just read that many characters for the string. And so there's similar ones for begin array and end array. We're skipping over white space and just looking for these JSON characters. And again, there's no intermediate buffering here. We're talking directly to the segment, which has come as the single buffering indirection from the socket or the file. Most people are not going to be interacting with the streaming API, although it does exist. There's also a class called JSON adapter, and this is probably what users of JSON or Jackson are most familiar with, This is object mapping, or data binding, it's sometimes called. This allows you to just put the JSON directly in a class which looks of a similar structure. And so the interaction here is basically you use the Moshi class, which is kind of the central point through which you do the reading and writing, to create this JSON adapter. And the way it creates the adapter is an implementation detail currently done through just reflection. And we can now take the source, whether it be from a socket or a file, and instead of getting back something that we have to parse, we now get back an instance of our object. Hopefully most people are familiar with this. It's basically the same thing as other JSON libraries you've seen. Oh geez, 5 minutes. Okay, Retrofit. I had a lot of content. Retrofit's a high-level HTTP client, and here it really serves to marry the two things that we've just looked at, OkHttp and Moshi. And because Retrofit is going to know about OkIO, it can really just marry the two, again, without any additional layers of indirection. So this is how you define a means of making an HTTP request. It's done through an interface in a declarative fashion. We create this object called the REST adapter, and the REST adapter just knows about the server, the base endpoint, for the relative URLs to be paired to. We create an instance of our interface. Again, implementation detail, currently done through reflection. And then we just have to call methods. We call methods, and Retrofit is going to take care of calling OkHttp, creating the request, unmarshalling the response with Moshi, and giving you back your presentation object. So right now it's a bit implicit, but behind the scenes we're creating defaults. We're just using a default OkHttp client. Here, if you wanted to, you could create your own for setting up, SSL, or you want to do caching. And then we have our converter. Retrofit is agnostic to the conversion means that you're using. So right now it's actually using JSON. It will eventually switch to Moshi, but there's really no timeline on that yet. There's also converters for Jackson, XML, protocol buffers, etc. Okay. Oh, this is perfect. This is my last slide. This is the most epic slide, by the way. Okay, so we're gonna zoom back, and we're gonna see how these are all interacting. And hopefully, I will not have to say that there's no additional buffering, even though there's layers of indirection here. I cannot stress that enough, because that's what makes all of this work. That's what really makes all of this so efficient, and why you should use all of these together, is because even though they're separate libraries, by building on top of the OkIO types and by the mechanism through which buffer allows you to move around data, it becomes extremely efficient. And you can even write something higher level on top of this, and as long as you're using the OkIO types as well, you're not going to pay any cost of indirection. So Retrofit is kind of the shim that sits between everything. It talks to OkHttp, who talks to our socket, who talks to the cloud. We saw in the examples earlier that there's these sinks and sources that OkHttp creates, which allow you to read and write the requests and response. The way that Retrofit talks to OkHttp is through its types, request body and response body. It's actually talking through requests and responses, but for the purposes of this, showing where the data flows, I'm showing the bodies. Retrofit has the converter indirection. It's not Moshi specific, like I said. So in this case, we're using the Moshi converter. The Moshi converter has a Moshi, which has the buffered sink and buffered sources that allow us to read and write the JSON. And then it also takes a type, an arbitrary Java type. As our example showed, this was our presentation object. This is your applications types. Retrofit, again, uses the OkHttp types to talk to the converter. So it's basically just taking the request body, or rather, I'm sorry, it's taking the response body for response and just passing it to the converter and saying, hey, read the data that's in this response body's buffered source. And you'll see it also has the T because it will pass in Java objects to be converted to JSON, and it will pull out Java objects that were converted from JSON. Our interface sits in front of this, which has our method that we define, and then there's just some implementation detail that sits between the generated class that backs our interface and retrofit itself. Okay, ready for some magic move and animation? Just to show how data flows through this system, when we make this call, and if we potentially pass in information, it's going to get marshaled off in, whoop, I forgot that was automatic. Maybe it's not. That's automatic. It's going to get passed through the system, through retrofit, into the converter, into Moshi. And this is your type. This is your data type, the Java type. It's going to make it directly into Moshi. Moshi is going to convert that into a buffered sync, an OkIO type. It's going to use OkIO to write that type back out somewhere. But that somewhere is linked all the way back through retrofit, into OkHttp, through a sync, and into the socket. So even though these are separated by layers of abstraction, by sharing the OkIO types, and in this case for retrofit sharing the abstraction that OkHttp has, even though there's these layers of indirection, it's really only writing basically through a single buffer. Through a single buffer. It's writing to a segment, and once that segment is full, it's going to get flushed down this pipeline automatically. So separated by a bunch of classes and a bunch of configuration, these things are still very tightly linked due to the OkIO types. And then we see the same thing in the other direction. When we're reading data from the socket, it gets piped all the way through, and even though Moshi is extremely separated from the underlying socket, it's going to be pulling data from that socket through only one layer of indirection, very efficient. And then we create our presentation type, and our presentation type comes out the other side. So these are the 4 libraries. They build on top of each other. They work very well with each other. They're not exactly a pyramid, but I really like the pyramid. And that's pretty much it. So you don't have to use all these libraries together, but hopefully as I've showed you that the way that OkIO works really lends itself to using types that are all using OkIO. If you do run into something that you want to use, say a different serialization mechanism, that's fine, because the buffered sinks and the buffered sources allow you to turn those into input streams and output streams. And while you are going to pay a little for doing that, by having still the other 3 pieces of this pseudo triangle there, they're all still going to gain much more benefit than otherwise. And that's it. So all these are available on GitHub. It's github.com/square/whatever library you want. And that's it. Thanks for attending. I don't know if I have time for questions. You probably have a lot. That was really technical. Anyone? Questions? Yes. Yeah, so it's not done, which is why there isn't. So what's the performance compared to competing libraries? It's not done, so we haven't run thorough benchmarks on it. It should blow away JSON just due to the underlying mechanism. And Jackson and JSON are interesting to compare directly because depending on the type of payload, one is actually faster than the other. So I suspect you'll see that Moshi wins in some benchmarks, and it's going to lose in other benchmarks just based on how Jackson is optimized and how Moshi is optimized. One thing we always say is that, and Retrofit does this automatically, is that you should stream your JSON directly to your serializer so that the cost that you pay for deserializing is like amortized over the cost of the network. So it's going to take 10 seconds to download a meg of JSON. And if you download your meg of JSON and then you do your serialization, you're going to pay that entire serialization cost. But if you're streaming the data directly from your HTTP response to Moshi, and Moshi can pull the data as it comes in, the cost of deserialization is going to be spread out over that 10 seconds, and you're really not going to pay that much overhead because it's going to be happening incrementally. When the network is like 10 to 100 times slower than the cost of serialization. So we'll be doing all that and showing stats and stuff. Because we do that streaming, we focus on that. Like I said, it's not hugely important for those benchmarks to always win. One of the things we are focusing on is actually just keeping the library small, keeping it simple, and making sure it's very clear how it behaves and that there's nothing surprising or really shocking in there that you wouldn't otherwise have to like write or deal with yourself. Anyone? Yes, Ty.
So with so many artifacts built on top of each other and make them work optionally together, how do you guys deal with transitive versioning help?
Yeah.
What kind of contracts do those characters?
So with basically all these libraries being separate, how do we deal with like versioning and transitive dependencies? So yeah, it's tough. So the retrofit that I actually talked about in this talk is non-existent. Is the hypothetical of version 2 that worked on, where for a loose definition of is being worked on, will be worked on, I guess. And basically, yeah. So retrofit has been the top level one. It's been the one that's had to deal with the problems of interacting with all your converters and interacting with all your HTTP clients, because it's been agnostic to both. So we have had growing pains where OkHttp 1 to OkHttp 2 has changed some of the APIs, and how do we support both of them at the same time? I mean, I don't know how to answer how do we deal with it. Slowly, carefully. One of the things that's actually changing with retrofit is that it's not going to be HTTP client agnostic anymore. It will explicitly depend on OkHttp, and that will be a requirement. And that's because retrofit was born in a time where there was no OkHttp and there was no really good HTTP client on Android. We had to sit between the Apache of 4.5 years ago and URL connection of an ugly API. And then OkHttp came along and we said, we want to be able to support all of these. And all of the wrappers and indirections that are in retrofit are now in OkHttp. So in retrofit 2, we're basically going to over half the size of the library just because those things don't exist anymore. Whereas if we didn't do that, we would have to deal with problems of supporting all of these things and running into kind of conflicts and massive transitive dependencies. OKIO is the tricky one. We maintain very strict binary compatibility because it is a transitive dependency of all these libraries. Retrofit wants to talk to OkHttp, and it wants to talk to Moshi. And it doesn't really know about OKIO, but OKIO is sitting underneath both of those. And if we all of a sudden rev OKIO to version 2 and only update OkHttp, we're going to be stuck not being able to talk to both of them. So we're taking a very careful and slow and like Guava-like approach where we're very conscious about forward compatibility. So any changes we make will be binary compatible at the very least, so that we won't run into transitive problems. But we might break source compatibility, which means you just have to recompile. If you update your dependency, you might have like a new checked exception that you have to catch or something. But that's pretty much it. We're definitely mindful of it because of this relatively complex graph. It is something to keep in mind. Yes.
Does retrofit support caching?
Does retrofit support caching? No. That's the HTTP client's job. This again goes back to like the responsibilities of the pieces of your application. Retrofit sits on top of your HTTP client, and we message it as a high-level abstraction on top of HTTP. So its only responsibility is creating requests, parsing responses, and passing it to your converter. That's all it does. Caching should live in your HTTP client. because your HTTP client is much more knowledgeable about how to do caching and how to talk to the remote server. So if we were to do caching in retrofit, there's things called like conditional caching. Sometimes we would have to deal with like authentication problems. OkHttp is the right place to do this because it can make multiple requests to the server. It can merge in-flight requests for the same resource. It's the place where you want all this to be happening. So we're actually going to be improving OkHttp's caching in the future. Right now it only caches responses, and there's other things like cookies and just like the knowledge we have about which servers to connect to that it'll be caching in the future. So that's really the right place for caching to live. And you'll see that in like URL connection on Android is where caching happens. So even there you get caching at the HTTP client level. Yes?
Why the Moshi is encryption based? And I think if the Moshi is application processor based, it's much more fast.
Yeah. So why is Moshi reflection based? One, for the reasons I said earlier about spreading the cost of serialization over the cost of the network. It's fast. It's pretty fast. If you're really at the point where you need blazing fast JSON parsing and writing, you could either use the streaming API of it or use an annotation processor-based approach of just a different library. I was careful to point out when I talked about the JSON adapter, the fact that it's implemented by reflection is an implementation detail. You can certainly implement a JSON adapter with annotation processing. We just haven't because we don't have that requirement of needing 1 to 2 millisecond serialization times. We can pay 12 to 15 milliseconds spread out over a whole second. But there's certainly the option, and that's exactly why that class is designed like that, so that you have the option of that could actually be a separate library that just generated JSON adapters. That would be a very easy like companion library or companion module to write. So we just want to keep the core free of that, but you still have the option of doing that. We just haven't done it. But I might. I've done that before. I might do that. Yeah. All of these libraries have nothing to do with Android. They all work on the desktop, or well, the JVM. All 4 of them. We use OkHttp, OkIO, and Retrofit on our backend services. And Moshi is just a Java library as well. Yeah, nothing Android specific about them. There are Android customizations that happen in OkHttp. Like it knows if you're running on Android and it will do things differently. It will tie into some of the platform APIs a little bit better, but it only does that when it sees it's there. Otherwise, it works perfectly fine in the JVM. Oh, yeah. Picasso. It is not. If I... so Picasso uses Android for all of its work. We basically just wipe our hands clean of image decoding, and we say that's Android's problem. Other libraries don't do this. If we hated ourselves and didn't like free time, we could re-implement image decoding based on top of OkIO. It would actually be really nice. One of OkIO's samples is parsing metadata from ping, I think. It's really nice. I don't hate myself enough to go through that process. And there's a lot of optimizations that Android can make that we can't make, or that we would have to write like a ton of native code, and I just don't want to do that. There would be an advantage of putting OkIO a bit closer to the bitmap decoding, but it's not going to get that much closer, and it would force us just to create a bunch of abstractions in Picasso that we just don't want to make. Somebody else can do that, I think. I don't think we'll do that, but I really don't know. But probably not. Oh God, yes. Yeah.
What do you think about programmability?
Volley. I like Volley. I know Ficus a bit. It's designed for a different purpose. It's very unopinionated and kind of wants to be applicable for a bunch of different tasks. So it has a lot of abstractions, and you kind of have to do some things yourself. And it's also born out of the necessity of the Android Market application, now the Play Store, running on every device. So it has a lot of things in it that work around Froyo and gingerbread problems, and it's a very nicely put together library. We're just more opinionated about certain things, and that's what gives us these 4 libraries. But there's nothing wrong with it, except that it uses Java I/O input stream and output stream. But otherwise, yeah, I mean it's fine, right? Like we actually don't really care if you use all 4 of these libraries. We would like for you to, but there's nothing wrong with using Moshi with Volley or whatever. You can use OkHttp with Volley as well. Yeah, it's just it's not really competing with any of these libraries directly, but it's also not competing with all of them together. I don't know. That doesn't really answer your question. It's a fine library, but it's just very unopinionated, and we have strong opinions, and because we have those opinions, we can make optimizations. And if you saw the keynote, Volley's a little bigger than it probably should be, and we like our 4 little tight circles of very focused, strong libraries. But yeah, yep. Any hope for Google embracing? Oh, do I have to go?
Maybe answer this one, then we have to take lunch, otherwise people might not be able to.
Yep, sounds good. Any hope for Google embracing this stuff? Do you mean like as exposed in Android as APIs? Okay, maybe. So with regard to Picasso, like, it's a very complicated system. It's actually mostly based on Skia, which is code that I don't think many people want to actually get in and mess with, which is why you haven't seen a lot of uptick on like modern image and video formats. Just kind of anecdotally on the side there, OkHttp is actually the HTTP client that backs Android's HTTP client. So JavaNet URL connection, if you use that API on Android, you're actually using OkHttp under the hood. And therefore, transitively, you're also using OkIO under the hood. Now, those APIs aren't exposed to you as an application. You still have to interact with Java URL connection, which nobody wants to do, and hence why you can bundle OkHttp as a separate library. So they're certainly cognizant of the fact that there are better solutions, at least with regard to the HTTP client. But with image downloading, or rather image decoding, I think it's just such a complicated and fundamental piece of the Android infrastructure around like the graphics pipeline and stuff, and native memory. There may not even be a reasonable way to expose it such that we could do something really nice. But we haven't, certainly nobody has been talking about it, so maybe it just needs brought up. But I think it would be a very complicated endeavor that might not have enough payoff to warrant doing that much work. But I just don't think anyone's ever brought it up. Okay, so lunch is happening, or has happened. So please go eat, and thanks again for coming.